I'm going to talk now about sleep and wake up. So a lot of times what can happen is threads are going to need to wait for some specific event or condition. So for an example, let's say we've issued an I/O request and now we're waiting for a disk read to complete. Okay? So we did a read, we issued a disk request, and now we're just waiting for that. Or we're waiting for, let's say, a pipe reader. So we've got a pipe, we've got a writer, we've got a reader. The writer is writing into the pipe, but the pipe has become full, right, with some buffer. And so the writer's waiting for the reader to read some of that buffer. Another example would be waiting on any child to exit. So we call the actual wait system call, and now we've got a parent process that's waiting for a child to exit. So it's waiting for some condition, for some event. When we're waiting, we don't want to spin lock, right? Because that just chews up CPU time. Plus, it may be that the CPU needs to actually be running some other thread in order to enable the waiting thread to continue. The example certainly of the pipe where the writer is waiting for the reader to read to make space. If the writer just sat there in a spin lock and didn't allow the reader to run, then they'd just be stuck. So what we're looking for are coordination primitives that will yield a CPU. And what we're going to be using in XV6 is sleep and wake up. Now, there are other coordination primitives you can use. Condition variables, barriers. We're going to see those in our in-class exercise, I think on day 12. Okay. But today, sleep and wake up. So what's sleep going to do? Sleep is going to have two parameters. A channel and a lock. Okay. And what does this do? Well, this is going to sleep on the channel chan, okay? And this is just an address. And we'll say that it sort of names the condition we're sleeping on. Okay. And then wake up is going to wake up all threads that are sleeping on chan. So it may wake up more than one thread, right? If multiple threads have called sleep on a particular channel, when you call wake up, all of them are going to come up awake. One thing to keep in mind is there's no particular formal connection to the channel that someone is sleeping on and what they're actually waiting to happen. Sleep can return even if the condition they are waiting on is true or false. Okay, so whoever calls sleep has to take the return of sleep as a hint that what they're waiting on may be ready, but it might not be. An example could be that if you had a pipe, which is implemented with a buffer, and you had a reader, and you had multiple writers. And this pipe becomes full. Each of these readers goes to sleep, and they all wait on the same channel. When the reader then goes ahead and reads some bytes from here, it would do a wake up on the same channel and wake up all these writers. Well, the first writer to be woken up might fill the pipe again. And then when these successive writers came awake and looked, they would find that that pipe is still full. So as far as they're concerned, it was full when they went to sleep. They woke up, it's still full. So the caller has to treat the fact that it's returning as a sleep and actually as a hint and actually check to ensure that what they're looking for is true. So they're all going to write their code something like this. While the condition of interest is not true, sleep. We'll talk about this lock in a bit. But it's important to realize that this is how it works. And theoretically, I guess, you could just have a single channel, right? You can imagine no channel. And what wake up does is just wake everyone up who's waiting for anything. And then all of them would go through and check to see whether the condition is true. And if not, they would go back to sleep. So the channels are just an optimization to reduce the number of threads that have to wake up on a wake-up call. But all of them still have to check that the condition they're looking for is true. And if it's still not true, go back to sleep. So now let's look at some code from XP6 that uses wake up and sleep. So we've got IDERW. So IDERW is issuing a read or write request. So it acquires the IDE lock and then goes ahead, and this is the condition it's looking for. So it's looking to see whether the B flags and valid is not equal valid. So basically, it's looking for the flags to be valid. And while that's not true, it's sleeping on that IDE lock. And once it's done, it releases the IDE lock. The interrupt routine, right? So this is basically being called because we had an IDE interrupt. So it's going to go ahead and acquire the lock and then set the flags to be valid and to not be dirty. And then go ahead and wake up whoever's waiting. So what channel are we using here? Well, the channel we're using is the pointer, which is the actual buffer that's of interest. So whatever this buffer is that we are reading or writing, the interrupt routine is going to tell us about that buffer. So the question comes up, though, the caller, IDE read write, is holding the IDE lock as it goes to sleep, as it calls sleep. But that's a problem because the IDE interrupt needs to acquire it. So shouldn't IDERW go ahead and release the lock before calling sleep? And the answer is no, right? As you can imagine, it's written that way for a reason, and if it were written differently, it wouldn't necessarily work. So let's kind of look at what would happen. So let's go ahead and say that's what occurred. So let's say we have a broken sleep. It's broken sleep because it doesn't actually take a lock as a parameter. Okay, and so this is the code that doesn't work right. It's going to go ahead and acquire the lock, and then it's going to, before calling sleep, call release of the lock. So here's what could happen. Imagine that this code goes ahead and then calls release, okay? But before it actually calls sleep, the IDE interrupt fires. So what's happened is it's done some request, and the request is very quick. And so after the release, but before this thing goes to sleep, the IDE interrupt goes off. It is able to acquire the lock. It goes ahead and sets these and then calls wake up. The problem is, what's wake up going to do? Wake up's going to just iterate through the process table, again, of course, having the process table lock, and look and see, is anyone sleeping on this channel of interest, of the wake up channel? And if so, make it runnable. So make it wake up. So it wakes up everyone who's waiting on that channel. The problem is this guy's not yet waiting on the channel. It's given up the lock, which has allowed the interrupt routine to go ahead and acquire the lock and do the wake up. So there's a problem. We have what we call a lost wake up. And the problem is now this guy's going to go to sleep, never to be woken up, because the IO team has already finished. There's no one that's going to call wake up on it. So it goes to a permanent sleep. Instead, what we're going to do is have a non-broken sleep, right? So we're going to go ahead and pass in the lock. We're going to pass the lock here. So we are going to pass in the lock, which we have to be holding. Okay? So we're required when we call sleep to be holding a lock. And what sleep is going to ensure is that that lock gets released only once we are sleeping, or rather, only once we're far enough along that by the time a wake-up happens, we'll be asleep. Okay, so it's going to go ahead and acquire the process table lock because it's going to be modifying one of the processes in the process table. Once it acquires the process table lock, it's then free to release the sleeping lock, the spin lock, because it knows wake up can't actually go through here until it has acquired the process table lock. So it's safe throughout this duration of wake up actually going through, okay, because it's going to be blocked here. So then it goes through, it can update the channel, update the state, and then go ahead and call schedule, right? Where again, schedule is going to switch to the scheduler. This particular thread is going to be asleep, and the scheduler will go run other threads. When the schedule returns, then we're no longer sleeping, right? We've been woken up. If it returns, we're running, so therefore we can't be asleep. We go ahead and set the channel to 0 because we're not waiting, we're not sleeping on anything. We go ahead and release the process table lock. Again, remember, schedule kind of transfers the process table lock over to the scheduler, and then scheduler transfers it back to us as we are yielded to. And then once we have released the process table lock, we reacquire this lock. Okay, it may take some time to reacquire this spin lock. We may be in an interrupt routine here, or what could be very likely is we've got another process or another thread that is running the same sort of code, right? That is waking up. So we might not be the first to wake up. If we're not the first to wake up, another's woken up. It has gotten a lock before we do, and so we're waiting to acquire that lock. We then come back and the sleep finishes. We are holding the IDE lock. We go back to the beginning of the loop and we check, is our condition satisfied or not? We've seen situations where the condition may not be satisfied and we have to go back to sleep. In this particular case, we were the only thread that was sleeping, and so we find that this condition is true, and then we can go ahead and release our IDE lock and return from this IO routine, basically with the IO finished. It's useful to look at two different situations. Make sure that when a sleeper sleeps first, that then the waiter will correctly wake it up, and also that the waiter doesn't run before the sleeper's completely asleep. So let's look at what happens. So we have here the sleeper, and assume that it's going. So first, a sleeper has the lock. So this lock extends, let's say there. And then there's also the p-table lock. During the duration of either of these locks, the waker is not executing the wake-up code, right? Best case is at the very beginning of the wake-up code if it's waiting for p-table lock. If it's waiting for this lock, it's actually in whatever code is before calling wake-up. But it is blocked through this entire time. And only at that point then can the waker run, and the waker will first obtain the lock, and then within wake-up will obtain the p-table lock. So the waker holds the lock for the its entirety, and within that calls wake up, and wake up holds the p-table lock. So this portion is within wake up, just like this portion is within sleep. Okay, so that's one possibility of what happens. Okay, so this is kind of if the sleeper goes first. Now there's another possibility, right? The other possibility is the waker runs first. So let's look at that case. So the waker runs first. The waker runs first, and it goes ahead, of course, and gets the lock, and as part of calling wake, calls p-table lock. But the sleeper has not issued a sleep request yet. So therefore, there's nothing to wake up. Now, the sleeper can go ahead and get the lock, right? It was blocked off. Sleeper could not be checking its condition because it didn't have the lock. So now, the sleeper, or let's call it the potential sleeper, obtains the lock. And at this point, now has the lock checks the condition is true because the waker set whatever that condition is. And so the sleeper then says, I don't even need to go to sleep because my condition is true. But note that it couldn't check the condition unless it held the lock. And therefore the waker can go ahead and set the condition here, right? Because that's what the waker's doing. The waker sets condition. The waker here sets. So in this case, the sleeper doesn't even bother going to sleep because as it gets into its loop of checking the condition, it checks the condition, it's true, it doesn't bother to go to sleep. In this case, the sleeper checks the condition is false, it goes to sleep at some point later on, but certainly no earlier than after the sleep is completed. Then the waker can go ahead and obtain the lock, wake up the sleeper, at least mark the sleeper to be woken. It's not going to actually run and acquire the lock until it gets to here. And then the waker is going to set the condition. So by the time the sleeper, again, obtains the lock for the second time, then it goes back and checks the condition and sees that it's true. Next time doesn't have to call sleep. So that is how, assuming that there are no other situations happening, no other threads waking up, then this sleeper will find the condition is true. But if it doesn't find the condition is true, it just goes back to sleep. There are many coordination primitives that exist. So other coordination primitives that exist are, let's say, counting semaphores. So these have the advantage that they will just wake one particular sleeper. Okay? Or you can choose how many, really. Condition variables, which we'll see in an in-class exercise. Wait queues are used by the Linux kernel. One disadvantage of this sleep wake up is the possibility, if you have a large number of processes who are waiting, sleeping on a particular condition variable, that when you wake up on that condition variable, you get what's called the thundering herd. So you have all these threads that wake up and they come and they try and check their condition. And one of them finds it's true, and the rest of them find it don't, and they'll go back to sleep. So this thundering herd of threads that wake up and then go back to sleep. At least most of them go back to sleep. So they are more complicated type synchronization primitives can help avoid that. So let's look at another example. We've got pipe read and pipe write. So keep in mind we've got this buffer. So we've got a buffer for the pipe, a fixed size circular buffer, and the reader is reading from the buffer and the writer is writing into the buffer. So the reader can't read if the buffer's empty, the writer can't write if the buffer is full. So what's the writer going to be doing? The writer is going to go ahead and acquire a lock on the pipe, right? So the pipe, we're going to have a lock associated with it. It's going to acquire the lock, and then it can just go through the number of characters that are supposed to be written. And for each one, what's going to happen is in write tells us where we are in the buffer, and in read tells where the reader is in the buffer. And so basically, if they are on top of each other, then we go ahead and see, well, actually, is anyone have a reader open on this, right? You know that pipes can have multiple file descriptors open, even across multiple processes, that might be reading from this buffer. If none of them are open, or if this process has been killed, we're going to go ahead and get out of here and return a -1 from the pipe write. Okay? Otherwise, then we know the pipe is full, right? If the pipe is full, then we're going to go ahead and wake up the reader. So we're going to use the address of where the reader has read to as the channel. That's for the wake up, because we want to wake up all possible readers and say, go ahead and start reading, this buffer's full. Okay. And then we want to sleep on the write address, okay, the address of where we are. And notice we are holding the lock. When we wake up, we have to go back in and check. We might still be full. Right? For example, we might have had another writer wake up before us and write in and fill it up again, even though our reader did read something from it. So in it, we're always using the standard while loop of check our condition, and while the condition is not true, go ahead and do a sleep. If that'll succeed, then we want to go ahead and actually write something in the buffer. So we write a character in the buffer, and then we go back again until what? Until we've written all the characters that we were asked to write. Once we've written all the characters we were asked to write, we again go ahead and wake up any readers, because there may be people waiting. We release our lock and return the number we wrote. On the reading side, what's going to happen? Again, we acquire the lock, and now it's slightly different. This is checking whether the buffer is empty. Okay, so if the buffer is empty, then we are going to want to sleep. Now, we check something as well, which is we're going to check whether there are any writers open. Okay. If there are no writers open, that's how we know we have end of file. You may remember from an in-class exercise where we were setting up pipes that if the parent process, that is the shell process, did not close the right end of the pipe, the right file descriptor, that the reader would never finish because the reader never got an end of file. So everyone has to close the right end. All the open right ends have to be closed in order for a reader to see an end of file. This is a slightly different format in read than in write. And the reason is that the way read is documented is it will read whatever is there and return those number of characters. So no more than are asked for, but it may return fewer. So let's give an example. Let's say there are 6 characters in the buffer so far when a pipe read is done. Then we'll acquire the loop. The buffer's not empty. There is still a write open. We will go ahead and go through and actually we don't care about checking if the write open because read, we don't have an empty buffer. And so then we go through and for I equals 0, I less than 6, we're going to go keep reading. Again, if the buffer is empty, we're going to break. And the percent pipe size is for the wraparound because it's a circular buffer. So let's kind of just see what is going to happen. We have an on-empty buffer. We're going to go ahead and read those characters, wake up any writers because we've consumed some space, release our lock, and return how many we read. So again, if there are characters in the buffer, we will read them and return how many are there, not to exceed the number requested in. On the other hand, if the buffer is empty when we enter, then as long as it's empty and there are writers, then we will go ahead and first check and see, well, wait a second, have we been killed? All right. And so we'll go ahead and release our lock and return. So this is one of the cases where we might have been killed and we don't want to just be sitting in here forever waiting. So we go ahead and return. And then we'll just sleep, waiting again on the same channel that a writer might wake us up with. So we will go into this loop. We'll go to sleep. When we wake up, we'll check our condition. Is there anything in the buffer? Right? If it's empty and there are still writers, we'll go through this loop again. We'll keep going until it's non-empty. Once it's non-empty, we will read what's there and then go through. And let me just show you, by the way, the in-read and the in-write. So in-read is some index into here, and in write is some index into here. So in write is always writing, and in read is sort of reading behind it. And if they ever are equal, that means the buffer is empty. And if the writer is page size ahead of the reader, that means it's full. As you can imagine, it can be tricky to get this code to work just right. So this can be a complicated coding dealing with locks and synchronization. It's easy to get wrong, especially as you're first learning to deal with it. So what about terminating a sleeping thread, right? We have told it to kill. We're going to just go ahead and set its kill to 1. We can't just forcibly terminate it. So it might be executing in the kernel with a kernel stack. It might be in some critical section, and we need to actually restore the invariance. So we can't just immediately terminate it. Instead, what we say here is exit at the next convenient point. All right, when is that convenient point going to be? That's going to be no later than the next system call or the next interrupt. So as we look at what's going to happen in the trap handler, if once a trap occurs, if we're in a system call, if it's killed, we'll exit. Then we run the system call. Something in the system call itself may cause us to be killed, and so we'll check there. And then we'll also check on any other trap that occurs. And assuming we were in user mode at that point and we are killed, we'll go ahead and exit. And as we said, that exit will go ahead. And so what are we going to do here? We're going to wake up the parent, right? How many parents are there going to be? That is, how many waiters are there going to be on this channel? How many sleepers on this channel? Well, there's just going to be 1. And that might be the parent. And then we're going to go through and wake up the init proc. And we may wake up the init proc multiple times, but that won't hurt. And then we'll go ahead and set our current state to be a zombie. So what if we are told if a sleeping process gets killed? In that case, well, what could it be sleep? Why could it be sleeping? It could be sleeping and waiting for console input. It could be in a wait. It could be in IDERW. And so we want to go ahead and wake it up. We'd like it to exit immediately, but maybe it's in the middle of some operation that it's halfway through some complex operation. Let's say that it's important to finish. In the case, let's say, of a pipe write, it's not important to finish, right? So we're going to just go through every time we're asleep and we wake up, we'll check and see. If we're killed, we're going to go ahead and bail out of here. On the other hand, in IDERW, we're not going to be checking that. We're only checking to make sure that our block has been read or written. We don't want to bail in the middle because there may be other operations that are happening. Maybe this is one of a sequence of blocks that has to be written. So we need to once we've written one, it's really important that we finish writing the other few. And this might be one in the middle. So we've already started reading, we've got to finish. So we're going to complete this sequence of operations. Once that sequence of operations is complete, right, this was generated by some syscall. So that syscall, when we get to the end of the trap handler, we will check, are we killed? And if so, we'll go ahead and exit. So here's the specification for kill. And this is, if the target is in user code, then we're going to exit on the next system call or interrupt. If the target is in kernel mode, and by kernel mode I mean we're actually executing kernel mode, then we won't ever execute more user code. But we may spend a while in kernel mode. And note that these rules are for xv6. Okay? That's how xv6 works. xv6 does have some system calls that take quite a while. JOS, on the other hand, doesn't have any such system calls, so it has different rules and certainly won't spend a while in kernel mode. So in JOS, interrupts are disabled in the kernel. So we can't have a wake up that sneaks in between a condition check and a sleep. And the termination, there's only a few system calls. They're very simple. There's no big blocking operations. There's no file system in the kernel, in fact. The file system is in user mode. So there's only really one blocking call, and that is IPC receive. IP receive leaves the environment in this not runnable state. So while you are waiting to receive, it's in this not runnable state, and the state it's in, it can easily be destroyed. So there's no existing code that needs to run, so it can just safely kill it.